There's a number. It isn't a big number. It doesn't look dangerous. It sits inside an equation you've probably never seen, written in units most people have never heard of. But this number, this single measurement, is quietly threatening to undo a century of physics. Understanding how the universe was born, how it evolved, and where it is going, we call for the past 100 years, we have been building a model of reality, a framework for the standard model of cosmology. And for a long time, it was one of the greatest intellectual achievements in human history. It was elegant. It was precise. It agreed with observation after observation after observation. And then we built a better telescope. What the James Webb Space Telescope found when it turned its golden mirrors toward the sky did not confirm our understanding of the universe. In some places, it contradicted it. And the deeper it looks, the wider the cracks become. This is a story of what happens when the universe stops agreeing with us. To understand the crisis, you need to understand one thing. The universe is expanding, not exploding outward from a central point, not rushing through empty space. The fabric of space itself is stretching, carrying galaxies apart from one another the way raisins in a rising cake move apart, even though none of them are moving through the dough. This expansion has been known since the 1920s, when astronomer Edwin Hubble noticed that distant galaxies were moving away from us, and the farther away they were, the faster they receded. This relationship is captured by a single number, the Hubble Constant. The Hubble Constant, usually written as h0, measures the rate of that expansion. Specifically, it tells us how fast galaxies are moving away from us for every unit of distance between us and them. The units are kilometers per second per megaparsec. A megaparsec is 3.26 million light years. So the Hubble constant is asking, for every 3.26 million light years you look outward, how many kilometers per second faster is a universe flying apart? It is at its core the speed of the universe itself, and we cannot agree on what it is. This isn't a new disagreement. When Hubble first calculated the constant in 1929, his estimate was so far off that it made the universe appear younger than Earth's oldest rocks. That was a problem. Stars cannot be older than the universe they live inside. For decades afterward, two rival camps of astronomers battled over whether the true value was closer to 50 or closer to 100. The war was fierce. Careers were built on one side of the argument. Reputations were staked. Papers were written with barely disguised contempt. By the early 2000s, the fight seemed to be over. Advanced telescopes had allowed both sides to converge on a number around 70. The dispute was settled. Cosmology could move on. It didn't move on, because as instruments got more precise, a new disagreement surfaced. Smaller than the old one, but far more troubling, because this time, both sides could show their work. The first method looks backward in time. In the early 2000s, the European Space Agency's Planck satellite spent 4.5 years mapping the cosmic microwave background, the faint afterglow of radiation left over from when the universe was just 380,000 years old. That map is essentially a photograph of the universe in infancy, a snapshot frozen in light. From that map, physicists used a standard model to extract the precise conditions of the early universe, then projected those conditions forward through nearly 14 billion years of expansion. The result, the universe should be expanding today at about 67 kilometers per second per megaparsec. Clean number, tiny margin of error, sky-high statistical confidence. The second method is more direct. Instead of modeling the past and projecting forward, it measures the present. Astronomer Adam Riess, a Nobel Prize winner at Johns Hopkins University who co-discovered that the universe's expansion is accelerating, leads a team called SH0ES. They use something called the cosmic distance ladder, a chain of overlapping measurements that extends outward from our own neighborhood into the deep universe. It starts with pulsating stars called Cepheid variables. These stars breathe, expanding and contracting in a regular rhythm. The period of that rhythm is directly tied to the star's true luminosity. Measure the pulse, calculate the true brightness, compare it to how bright the star appears from Earth, and you can calculate exactly how far away it is. Physics, not guesswork. From there, you step outward to galaxies that contain both Cepheids and a special type of exploding star, the Type Ia supernova. These supernovae are nature's standard candles. They all detonate at roughly the same peak brightness because they're all triggered by the same physical threshold. Once you've calibrated them using Cepheids in nearby galaxies, you can spot them hundreds of millions of light years away and know exactly how far they are. Combine that distance with how fast those galaxies are receding, and you've measured the Hubble Constant directly. Riess's team got 73 kilometers per second per megaparsec. Not 67. 73. 6 points of difference. That sounds small. It is not small. In a field where measurements are routinely precise to within 1%, a gap of 8 or 9% between two independent methods, each using entirely different techniques on entirely different data, is enormous. It's the difference between a universe 13.8 billion years old and one that might be more than a billion years younger. It changes the size of the observable universe. It changes the rate at which galaxy clusters are separating. It potentially changes the nature of dark energy, the invisible force responsible for pushing everything apart. Think about what it means to redraw the timeline of everything. The age of the first stars. The moment when heavy elements were forged inside dying suns and scattered across the cosmos to eventually become planets, oceans, and the atoms inside your body. All of it depends on that number. You're not adjusting a dial. You're redrawing the entire history of existence. The disagreement between the two measurements has a name. Scientists call it the Hubble tension. And in 2019, Nobel laureate David Gross told Adam Riess to stop calling it tension. He said the field should call it what it is, a crisis. The most popular explanation for the Hubble tension was simple and reassuring. Someone had made a measurement error. Cepheid variables, the foundation of Riess's distance ladder, tend to live in the dense, dusty spiral disks of younger galaxies. When the Hubble Space Telescope looked at them, there was a concern that its cameras were blending the light of nearby stars together, a phenomenon called crowding. If nearby stars were contaminating the Cepheid measurements, the pulsating stars would appear brighter than they really were. Brighter apparent brightness equals closer calculated distance. Closer distance equals a higher measured expansion rate. Fix the crowding. The argument went, and the Hubble constant would drop back into line with the standard model. It was a clean, elegant solution. It kept the standard model intact, and it gave the field something to look forward to. The James Webb Space Telescope was coming, and it would settle the argument once and for all. The James Webb Space Telescope is, in almost every meaningful sense, the most extraordinary scientific instrument human beings have ever built. It orbits the Sun from a vantage point 1.5 million kilometers beyond Earth, far from the thermal interference of our planet. Its primary mirror is 6.5 meters across, plated in gold, optimized to collect infrared light with a sensitivity that makes the Hubble look, in Adam Riess's own words, like a pair of reading glasses. Most importantly for this dispute, infrared light cuts through dust and crowding with precision that optical telescopes cannot match. If stellar crowding was contaminating the Cepheid measurements, Webb would see it. The pulsating stars would appear dimmer through Webb's cleaner eyes. The calculated distances would stretch, and the Hubble constant would fall. Some astronomers were already writing the obituary for the crisis before the data came in. The data came in. Webb confirmed Hubble's numbers. Not approximately, almost exactly. The Cepheids looked the same. The distances held. The expansion rate stayed at 73. In early 2024, Riess's team published a landmark paper in the Astrophysical Journal Letters, announcing that they had now used Webb to span the full range of Hubble's Cepheid observations, extending observations out to a galaxy called NGC 5468, about 130 million light years away, cataloging more than 1,000 Cepheids across 5 host galaxies and 8 supernovae. The conclusion was unequivocal. Measurement error could be ruled out with very high confidence. Riess put it carefully, as he tends to do, with systematic errors now thoroughly examined. He said, "What remains is a possibility that we have misunderstood the universe." By December 2024, the team's largest Webb study yet, drawing on 2 full years of telescope data, used 3 independent methods to cross-check their distance measurements. Cepheids, carbon stars, the tip of the red giant branch. All 3 agreed with each other. All 3 pointed to 73. But not everyone is convinced the tension is even real. Wendy Friedman, an astronomer at the University of Chicago and one of the most respected figures in the field, has spent years building an independent distance ladder that relies less heavily on Cepheids. Her team uses additional types of stars, red giants in a class called JGB stars, found in less crowded regions of galaxies, and therefore less likely to be affected by dust and blending. When Friedman submitted her own web analysis in August 2024, her three methods gave different answers. The red giant and JGB methods landed around 68 to 70, consistent with the standard model. Her Cepheid measurement came in near 72. Her overall combined results sat at about 70, no man's land between the two camps. Nobel laureate Saul Perlmutter, reviewing Friedman's data before its release, noted something striking. Her results suggested there might be a tension within the star-based measurements themselves, before you even compare them to the cosmic microwave background. That's a different kind of problem. It means the distance ladder itself, the tool astronomers have relied on for a century, might have unresolved issues at its foundation that no single telescope can fix. Riess pushed back. He argued that Friedman's team had used a small and potentially unrepresentative subset of supernovae, which could bias their results downward. The disagreement between the two camps has become one of the most closely watched rivalries in modern astrophysics. Two teams, both brilliant, both meticulous. Same sky, different answers. If Friedman is right, the crisis is softer than it appears, a puzzle awaiting a technical fix. If Riess is right, the standard model is missing something fundamental. The whole field is watching and waiting for the next data release. The Hubble tension would have been enough, but Webb delivered a second blow. Almost as soon as the telescope started observing, it began finding galaxies in the early universe that had no business being there. Not small, dim, infant galaxies, which is what the standard model predicted we would see at those distances. Massive ones. Galaxies seen as they existed just 500 to 700 million years after the Big Bang, some of them rivaling the Milky Way in mass. A galaxy that took our own cosmic neighborhood 13 billion years to build had apparently assembled itself in under a billion. Astronomer Mike Boylan-Colchin at the University of Texas at Austin ran the numbers. He showed that 6 of the earliest and most massive galaxy candidates spotted by Webb pushed right up against the absolute limit of what the standard model allows. To form galaxies that fast, nearly every available atom in their surrounding dark matter halos would have had to convert into stars. In a normal universe, that conversion rate sits around 10%. 90% of the gas never gets around to forming anything. It's too hot, blown outward by radiation, or simply drifts without condensing. These early galaxies seem to be running at 100% efficiency, a factory that somehow converts every gram of raw material into finished product with zero waste. Physics doesn't work that way, not in any model anyone had built. The initial reaction in the field was, frankly, alarm. If galaxies this massive really form this quickly, then either our models of galaxy formation are deeply incomplete or the standard model of cosmology itself needs revision. Then came correction. Graduate student Catherine Chworowski, working at the University of Texas, led a study published in mid-2024 that re-examined the data. She found that many of the apparently overmassive galaxies were being deceived by their own black holes. These galaxies, nicknamed little red dots for their color and compact size in Webb imagery, hosted black holes that were actively and voraciously devouring gas. The friction from all that infalling material heated it to extreme temperatures, and that heat radiated outward as intense light, blending with the starlight of the galaxy itself. It made each galaxy appear far brighter than its stars alone could justify. From billions of light years away, a galaxy with a ravenous black hole at its center looks almost identical to a galaxy with 10 times more stars. The telescope sees brightness, and brightness is normally a reliable proxy for mass. But here, the black hole was doing the work of billions of suns, inflating the galaxy's apparent size, like a searchlight attached to a candle. Once those little red dots were removed from the sample, the remaining galaxies fit within the standard model predictions. Chworowski's advisor, Stephen Finkelstein, was direct about the conclusion. There is no crisis in terms of the standard cosmological model, not from the galaxies. But the story didn't end cleanly. Even after removing the little red dots, Roughly twice as many massive galaxies remained as the standard model expects. Not enough to break the model, enough to bend it. Jaworski suggested that stars may have formed faster in the early universe than they do today, that the denser conditions shortly after the Big Bang made it harder for gas to escape during star formation, allowing the process to accelerate. A reasonable explanation, one that still requires adjustments to how we think galaxies assemble themselves. And then in early 2025, Webb found something even stranger, a massive spiral galaxy, quickly nicknamed the Big Wheel, that existed within the first 2 billion years of the universe. Spiral structure takes time to develop. It requires relatively calm, orderly growth, not the chaotic merging you'd expect in a young universe still violently assembling itself from raw gas and dark matter halos. Astronomer Thamia Nanayakara, part of the discovery team at Swinburne University of Technology in Australia, noted that the galaxy must have either assembled its mass in an unusually neat way, or formed most of its stars in place without the violent collisions that typically build large galaxies. Either explanation challenges conventional thinking. Meanwhile, a separate Cambridge team used Webb to study over 250 galaxies from that same early epoch and found the opposite pattern. Most of them were chaotic, turbulent, clumpy systems, adolescents that hadn't yet settled into smooth rotating disks. So the early universe contained both messy, chaotic adolescent galaxies and at least one remarkably mature spiral, coexisting in the same era. That is not a contradiction. The standard model handles gracefully. Set aside the expansion rate. Set aside the early galaxies. There's a third problem, and it concerns the shape of the universe on the largest scales. A study published in Nature Astronomy in late 2025, led by Alvaro Pozo, and including researchers from MIT, Harvard, and Taipei, found that many young galaxies observed by Webb appear strikingly stretched out, elongated, like cosmic cigars. These prolate shapes don't match predictions from cold dark matter, the backbone of the standard model, the scaffolding on which all of large-scale structure rests. They do, however, match predictions from two alternative models, warm dark matter and wave dark matter. In these models, the filaments of the universe's large-scale structure are smoother, allowing gas and stars to flow along them in elongated streams rather than clumping into spherical halos. The galaxies that form inside them inherit that elongated structure. That distinction matters more than it sounds. Cold dark matter isn't just one ingredient in the standard model. It determines where galaxies form, how they cluster, and how the large-scale structure of the universe looks on the biggest scales. If dark matter particles are lighter or behave differently than the cold model assumes, the ripples from that change propagate through almost every prediction cosmology makes. It would alter the mass of galaxy clusters. It would shift the expected distribution of dwarf galaxies around larger ones, a distribution that has already been a source of tension for years. It would change how gravitational lensing bends light around massive objects. You cannot swap out the foundation of a building and expect the walls to stay where they are. And then there's the S8 tension. Most people haven't heard of this one, which is strange because it may be just as important as the Hubble tension. The S8 tension is about clumpiness. The standard model predicts a specific level of clustering in the distribution of matter across the cosmos. How much matter tends to clump together rather than spread out smoothly? When astronomers measure that clustering directly, they consistently find slightly less of it than the model expects. The universe is a little smoother than it should be. Riess has called it the little sibling of the Hubble tension. Less dramatic, harder to explain away. If both tensions are real, if the universe is expanding faster than expected and is also slightly smoother than expected, they may be symptoms of the same underlying problem. Two cracks running through the same wall. The standard explanations are beginning to strain. Dark energy, which makes up roughly 68% of everything that exists and is responsible for the accelerating expansion of the universe, remains a placeholder name for something we cannot identify, measure directly, or explain. We named it because we needed a name. We do not understand what it is. One hypothesis that keeps surfacing is called early dark energy, a hypothetical burst of extra expansion that occurred in the first few 100,000 years after the Big Bang, then vanished. If something like that happened, it would shift the Planck prediction upward, closer to 73, without breaking the other things the standard model gets right. Mark Kamionkowski, a cosmologist at Johns Hopkins who has helped develop this idea, has compared it to the universe receiving an unexpected kick shortly after it was born, a nudge that rippled forward through 14 billion years of expansion, altering the rate we measure today. Nobody knows if early dark energy is real. No one has detected it, but it is one of the few ideas that could solve the Hubble tension without dismantling everything else that works. The standard model isn't dead, not even close. It still explains the cosmic microwave background with extraordinary precision. It predicted the correct abundances of hydrogen and helium left over from the Big Bang. It accounts for the clustering of galaxies across billions of light years. No competing model comes close to matching its track record, but it is developing fractures that weren't there a decade ago. And the field knows it. New instruments are coming, and they are extraordinary. NASA's Nancy Grace Roman Space Telescope will conduct wide-field surveys specifically designed to study dark energy at scales Webb cannot reach. The European Space Agency's Euclid mission is already in space, mapping the geometry of the universe on a scale no telescope has attempted before. Future data releases from the Gaia Space Telescope will allow astronomers to calibrate Cepheid distances with geometric precision, potentially removing another layer of measurement uncertainty from the distance ladder. The Atacama Cosmology Telescope has already produced the most detailed ground-based map of the cosmic microwave background ever made, nudging the Planck estimate slightly upward, but not nearly far enough to close the gap. Every new measurement either deepens the mystery or edges us toward resolution. No one yet knows which it will be. Cosmology has been here before. In the 1990s, the field nearly collapsed under the weight of a different contradiction. Measurements suggesting the universe was younger than its oldest stars. That made no sense. Stars cannot be older than the thing they live inside. The crisis seemed fatal. Then came the discovery that the expansion of the universe was accelerating, driven by something invisible, what we now call dark energy. The whole picture snapped into focus. What looked like a fatal flaw turned out to be the shadow of something enormous that nobody had seen yet. That's the pattern with crises in physics. They feel like endings. They almost always turn out to be doors. Adam Riess put it carefully in December 2024, as he often does. The discrepancy between the observed expansion rate and the predictions of the standard model suggests that our understanding of the universe may be incomplete. Two NASA flagship telescopes now confirm each other's findings. We have to take this problem seriously. If you could somehow stand outside the universe and watch this moment, you would see a species on a small rocky planet, orbiting an unremarkable star in the suburbs of a mid-sized galaxy, using mirrors and mathematics to argue about whether reality is expanding 6% faster than it should be, and getting genuinely upset about it. That is either absurd or magnificent. I think it might be both. The universe isn't broken. Our map of it is incomplete. And the next version of that map, whenever it arrives, is going to be stranger and more beautiful than anything we've drawn so far. The equations will be different. The picture on the box will be bigger. And somewhere in those new equations will be the answer to a question we barely know how to ask yet. What is the universe? And why is it expanding faster than it should? We don't know. And that is exactly where science becomes magnificent.